Here are the solutions to one of the early problems from section 7.1. Here we're just trying to see what the distribution should look like for a given population proportion. That's this number. So this is our true proportion of people in the population who would answer yes to whatever question we're talking about. And so that and the sample size tell us what the standard deviation is. So all that's being asked here is mean and standard deviation. So in all cases, the mean, the center of our distribution, is just going to be the population proportion. The standard deviation, and you can see why this standard deviation of the sampling distribution, right, that's a mouthful, you'll see that referred to sometimes as standard error. I'll tend to say the standard deviation of the sampling distribution just because that's correct, but it's a mouthful. So when you see standard error, it just means the standard deviation of some sample statistic, whatever the sample statistic is in this case. So anyway, so standard deviation is this formula. So remember, it's p times 1 minus p over sample size, and that's all under the square root symbol. So that's equal. And so in this case, that's approximately p is 0.08 times 1 minus 0.08 divided by, in part A, it's 5,000. So that's a very big sample size. So if I do that, I get 0.03837. I don't have on here how many decimal places it wants. It surely will tell you when it gives you a box to type in how many decimal places you want. So that's the standard deviation. In B, obviously the mean is the same, so the standard deviation will be the only thing that's different. And so that's going to be, again, 0.08 times 1 minus 0.08. And in part B, our sample size is smaller. It's 1,000. Oops, there it is. There. And don't forget that all has to be under the square root sign. So if I do that, I get about 0.008579. Again, it'll tell you how many decimal places to enter in the computer system. And for C, same mean, mean's always 0.08. And now 500. So that's 0.01213. So notice that the standard deviation, when your sample size is larger, your standard deviation is smaller, right? And that's because in this formula we're dividing by sample size. What it means intuitively is that the bigger the sample size, the less variability there will be in the p-hats. So let me just draw for part C here. Let me just sketch the p-hat distribution just so we can put it in context. The problem doesn't ask this. I'm just trying to illustrate. The center of the p-hat distribution is our true proportion, 0.08. So that's the mean of the distribution. So that's the center. Right? That's what our mean means here. It's a normal distribution, symmetric. So the mean is the center. Typically, I go 1, 2, 3 standard deviations above, 1, 2, 3 standard deviations below. And so, so in part C, I could label these standard deviations. Let me just label this guy. The way we always do, we take our mean and we add a standard deviation to it. So if I do that, that value will be 0.092, something, something, something. So I'm adding about 0.01 each time. So the next value will be that plus another 0.012, so 0.104, and so on. So I can label those guys that way, and that gives me a sense for how the p-hats would be distributed if I were sampling 500 at a time. If you sample 5,000 at a time, this is much, much smaller. If you draw the same picture, now every time you mark a tick mark, you're only going over 0.003. And so, the p-hats are much more closely clustered around 0.08. So when we have a sample size of 5,000, we expect our p-hats to not vary very much. There won't be a lot of variability to them. When our p-hat is 500, then there's a little more variability. So the smaller the sample size, the more variability there is, meaning there's a wider range of values that we expect the p-hat to take. Remember, we expect most of our p-hats to be between within 3 standard deviations of 0.08. So the bigger the sample size, the less variability there is in the p-hat measurements.